So that's my pleasure to welcome accept to welcome our two guests for today, which are Mr. Rolla and Mr. Giovanelli. I'm sorry. It's okay. So, Professor, okay, I'm sorry for that's not a very good introduction. I'm sorry. So, that's really a pleasure. You will be given a talk about factor models analysis. So that's so I let you go, and it will be recorded and transmitted on Zoom. Thank you.
Okay, thank you very much, Professor Luca. Rolla, and we talk about
This, wait, I have to.
testing for the martingale property using martingale difference divergence function. Okay, this is what we want to test. Sorry. Let's change. Okay, this is what we want to test. This is the martingale difference, the martingale hypothesis. And from a nonlinear time series perspective, it is important to test if one series satisfies this condition, even if it is serially uncorrelated, so that in this sense we can discover the existence of nonlinear dependence in the conditional mean. Okay, we will construct a test for this hypothesis using the recently introduced martingale difference divergence function, paper from Shao in 2014. So martingale difference divergence function is a concept that is originated by another function, which is distance covariance. And distance covariance is a statistical measure that is capable of discovering any kind of link between two random vectors. So it's, in the sense, it's able to capture any form of statistical dependence between these vectors, be it linear or nonlinear. Okay, distance covariance, and let's say something about martingale difference divergence. Martingale difference divergence is one statistic that is from the same family of statistics, distance covariance, but let's say it reduces the scope in terms of testing, in terms of measuring, because rather than look at any kind of dependence, focuses on the narrower concept of conditional independence, as I will show. Okay, distance covariance as this property is also capable of finding any nonlinear links. In its standardized form, it can represent a generalization of the Pearson correlation coefficient. Okay. Yeah, they, as I said before, they belong to the same family of statistics. Distance covariance is able to find any form of dependence. Martingale difference divergence focuses on conditional independence. Okay, our aim is to use the martingale difference divergence to construct a test for the martingale hypothesis, so that we can find some martingale difference. We can find out if a series is indeed a martingale difference sequence. Okay. Some words about distance covariance. It has been introduced by Zachary Ritz and Baker of 2007. It's a measure of dependence between random vectors of any dimension, even to vectors x or y, any dimension p. It is constructed starting from the characteristic function. Here we have represented we denote as the the joint characteristic function of the two variables. And is instead the px and py will represent the marginal characteristic functions of x and y for parameters in the exponent of the characteristic functions t and s. Okay, distance covariance checks this hypothesis that the joint characteristic function equals to the product of marginals. This condition is satisfied if and only if x and y are independent. Okay. Starting from that concept of independence, Zachary Rizzo constructs distance covariance as this form of distance in a weighted space. So basically, this is the form they define. They introduce a concept of weight function in the statistic, in order to define the statistic. Okay, let's say how can we define it? Basically, what we get in general terms is this weighted norm of this generalized covariance term. Let's call it generalized covariance. Internet connection is not. Okay. So basically, we can rewrite distance covariance as is the norm of this generalized covariance term defined starting from the transformation of the variables, which is the exponent, the marginal exponential. Okay, and this is the weight function they define. Okay, there's a reason why they define this weight function. Okay, I'm not going to spend many words on that. This is the generalized covariance term I talked to you about. This is the standardized form of the statistic called the distance correlation, which takes values between 0 and 1. It takes value 0 in case of independence and 1 in case of perfect dependence between the two. Okay. And basically, this is a lemma, starting lemma is actually a reason. So they can solve by making that assumption on the form of the weight function. They are able to this lemma of solving the integral, so that in order when you consider distance covariance, you do not have to consider any integral term. Okay, so this is the form they get to the lemma and to the assumption on the weight function. They get to this form here. And starting from this, they define basically the empirical version of the statistic of distance covariance. So basically, how let's spend some words on this. Basically, they I'm not sure about that.
Okay, so just cut it and we will do mine.
Okay.
Cut yours.
Okay. So basically, the empirical version of the oh, sorry. Okay. The empirical version is da Zoom.
No. This you give me the sound. I'm sorry. I won't do it. minutes. Can you see if it works? Can you please go ahead and you can speak.
Okay. This is the sample version of the statistic. Basically, they given to random samples of the variables involved, x and y. We construct the Euclidean distance matrices of the sample. We get n by n Euclidean distance matrices. And then these Euclidean distance matrices are, according to the procedure introduced by Zachary-Aritz, are double-centered in this sense. They are centered by row, by column, and by total mean of the matrix. So in the end, what you do is you multiply the two double-centered Euclidean distance matrices element by element, and you sum up everything, and you have the sample version of the statistic. Okay, so this is martingale difference divergence, which is very similar in its formulation to distance covariance, introduced by Shao and Zhang in 2014. And we want to determine if we are not looking anymore at full dependence, we are checking for conditional mean dependence of y on x. So the definition, as you can see, is very similar. You have this integral here. You still have what we can define as a generalized covariance term in here, and you still get the norm of this generalized covariance. And the weight function is the same as in Zachary-Aritz, so it simplifies because we are just considering in this case one characteristic function, so just one parameter on which we are integrating. That's it. Then the two statistics are very similar. Okay, let's move to time series. So 2012 was the first to make an application of distance covariance into time series, and he defined the concept of auto-distance covariance, which again can be seen as an extension of auto-covariance or autocorrelation, if you wish, and again makes possible to distinguish between serial independent random variables and variables that are uncorrelated, but they still have some other form of dependence in higher moments. Okay, auto-distance covariance is defined like this. Let xt be a d-dimensional stationary time series. We have basically the same definition. In this case, we have the same definition of the statistic. We are just computing a statistic between xt and its lag xt minus j. And again, we have this covariance term. This one is important. Okay. The univariate case, under the assumption that xt is a strictly stationary alpha mixing time series with finite first moment, Fokianos and Pizzillo in 2017 proved the convergence almost surely of auto-distance covariance in sample to its population counterpart for a fixed lag value j. Okay. Let us introduce similarly the concept of auto-martingale difference divergence. Definition is the same as before, but we are here computing the, let's say, the generalized covariance between the variable xt and its lag xt minus j. And we are basically checking the conditional mean dependence of xt on the entire past information. Okay. From now on, we shall just focus on the univariate time series case. So the statistics will take this form from now on. We simplify, basically we obtain a simplification in terms of the weight function. Okay. Let us discuss a bit the martingale difference hypothesis. Martingale difference divergence at leg J will be zero if and only if xt is conditional mean independent of the xt minus j. This condition is satisfied, and we can use this this property to determine if a given process is a martingale difference sequence. We can exploit that in later developments. And okay, it is relevant to determine whether a given process is a martingale difference sequence, even though it's a white noise process, because one important topic is to discover if is to study examples of time series that have zero autocorrelation, but they have still some form of nonlinear conditional dependence in the mean. This is what we are looking at. Okay, and let us use auto-martingale difference as a difference divergence as a graphical tool in order to determine to have a first intuition of what could be its utility. Okay, let us consider a Garch 1-1 model like this. And for example, let us represent here the auto-martingale difference divergence function and the auto distance covariance function for various lags. We also have the autocorrelation function represented here. So you see for a Garch model, you have zero autocorrelation at all lags. The auto distance covariance function is able to find dependence, and but still being the Garch, a Garch process being a martingale difference sequence, auto-martingale difference divergence function does not find any dependence. This is an important property. If we instead consider one model like the bilinear model, we have that the bilinear model gives us some series that have zero autocorrelation, but still have some nonlinear dependence in the conditional mean. And this emerges by looking at the auto distance covariance and auto martingale difference divergence in here. Okay, you can see for the bilinear model, you have zero autocorrelation. But at the first leg, you have one signal of a positive of some dependence that is a nonlinear dependence. And indeed, by looking at auto martingale difference divergence function, what you see is that this is some form of nonlinear dependence in the conditional mean. Okay. In order to construct a test, we need to introduce the concept of generalized spectral density from Hong 1999. And Hong explicitly works on this kind of generalized covariance here, and works on these terms given by the difference of the characteristic function, the joint and the product of the marginals. Basically, what it does is to consider a Fourier transform of this generalized covariance. And under this condition, it gives us a definition the generalized of the generalized spectral density here represented. The generalized spectral density can capture our pairwise dependence. And so in contrast with standardized spectral density, this is in contrast with standardized spectral density as it is more limited to linear dependence. Okay. Okay, these are the assumptions made by Hong. XT is assumed to be a strictly stationary alpha mixing process. The first moment should be finished. These are the mixing coefficients, and then some assumptions about the kernel function. Okay. This is a sample estimator of the generalized spectral density. And basically how Hong defines it, he is using empirical characteristic functions. And here you see we are using a kernel, and the variable P is just a bandwidth variable or large order parameter in the kernel. Basically, under serial independence, the spectrum becomes a flat spectrum, which has this definition here. This is the sample estimator of the flat spectrum. Basically, what Hong does is to compare the definition of the two, the flat spectrum and regular spectrum, and he does it in this form of distance. And after some passages, basically what he gets, he eliminates completely the integration over the frequencies. He's left with this expression here, where integration is still on the parameters of the characteristic functions. And you can see basically what we have in this definition of statistic, that we have the norm component, the normal component we spoke about before. The norm component with the generalized covariance coming from characteristic functions. And this is basically what we are gonna work with, because as we saw, distance covariance and martingale difference divergence actually solve this term. So they give us an advantage in the sense because they offer us a way to avoid any integral computation. So basically, they give us a way to express Hong's statistic without any integration. And basically, this is what Phokianos does. Phokianos and Pizzillo, they do this basically. They use distance covariance to solve Hong's expression, and through this they find an explicit way to express this test statistic. Basically, they find an expression which is this, and this is the test statistic of serial independence that Phokianos defines. And this statistic is capable actually to find any form of serial independence in the data. Serial dependence in the data. Okay, one property of the generalized spectrum is that it can be differentiated at zero, and its partial derivatives can be used to test an array of more specific hypotheses. In this sense, we can just take derivatives of the spectrum and with respect to the parameters in the characteristic functions. And basically what we get is a modified version of this generalized covariance term here. Okay, I reported the M and L here. They are just the order of integration for the characteristic functions, let's say. The order of the derivation. So taking this order of derivation here, basically we get to this expression and this form of generalized covariance here, and this is basically what we have seen with martingale difference divergence. So what we get is that martingale difference divergence can cancel out this term, and in the same way of Furkianos, it can give us a way to simplify the test statistic. And basically, in this way, we can simply obtain a test statistic for the martingale difference hypothesis. Okay, this is our test statistic. And basically, we obtain this by just simplifying the normal term here with martingale difference divergence. It's very similar to a Fockiano statistic, and is obtained according to the same procedure, starting from Hong's original class of tests and Hong generalized spectral density theory. Okay, we make this assumption. Again, we assume that XT is a strict stationary alpha mixing process. What we change here will require a stronger condition on moments, and then everything is basically left the same as before. And it's possible, we are able to prove that under those conditions, the sample version of martingale difference divergence in time series converges to its population analog, almost surely. Okay, still based on Hong, we can define a standardized version of the statistic. We have here the definition of the statistic introduced before. These are the standardization terms. And basically, okay, let's see. Okay, basically, under the assumption that the data are IID, this standardized version goes in distribution to a standard normal. The point here is that the fact that we require data to be IID in this case represents a limitation, as we are checking for the martingale difference hypothesis. We want to check for martingale difference sequences. So the fact that in order to get standard normal distribution, we require IID in the data, that's a strong limitation. Okay, this is another theorem. Goes to this in probability. And okay, let us discuss the empirical properties of the test. We basically, what we do is we approximate the limit distribution of the statistic using a wild bootstrap procedure as described in Fockianos. Basically, what they do, they generate sequences of auxiliary random variables. Let's call them W. And basically, The procedure goes like this. We have the sample version of martingale difference divergence. It's very similar to the sample version of distance covariance, and it's based on the same concept. We have Euclidean distance matrices. We double center them by row and by column, and then we take the product element wise and we sum everything up. The way in which we can perform our bootstrap is to just okay, let's say we can intuitively we can just re-express the sample version of the statistic like this. Okay, saying okay, this is a unitary vector. Okay, then this gives this is the element-wise product of the two matrices. Okay, and this gives us a double sum. The bootstrap is computed like this. It's computed like this. Once we have these auxiliary vectors, we can pre-multiply and post-multiply for the element-wise product of the two statistics, and we have a double summation weighted for the elements in the auxiliary vectors. Now let's discuss some size properties for the statistic. Under the null hypothesis that the process is a martingale difference sequence, we have this. Let us discuss some processes that are martingale difference sequences. The Garch process and the Arch process. We use this. We simulate these processes and we get these results. This is for the Garch 1-1, and we can see that we have different values of the bandwidth parameter in the kernel here, and we can see that the values 5 and 10% are always attained by the statistic as we increase the sample size. The table shows the empirical rejection probabilities 5% and 10% nominal levels. We have used two kernels, Parsen and Bartlett kernels. So we have defined two different scenarios for the kernel, different bandwidth values of the bandwidth parameter here. The p-values are obtained on 499 bootstrap replication for 1,000 simulations. Okay, the same results for the Arch process here. And even in this case, we approximate well the nominal levels. Okay. Power properties, we discuss a bilinear process and a threshold autoregressive process. And okay, this is the case for the bilinear model. You can see that increasing the sample size, you get to the value of 100. And okay, we have reported different sample sizes, different values of the bandwidth parameter. Again, the p-values are obtained on 499 bootstrap replication for 1,000 simulations. And for smaller values of the bandwidth parameter, we get a better approximation, let's say. We do not get to 100 for larger values. Okay, these are the empirical power levels for the threshold autoregressive model for the Parsen kernel. In this case, the 100 is approached much faster than in bilinear model. It still works. Okay, some some empirical examples. This is Standard & Poor's 500 excess return series. And okay, I've reported below the values of the autocorrelation function and of the auto-distance covariance function. As you can see, there's not linear dependence there's not linear serial dependence. The auto-distance covariance function can find some form of nonlinear dependence, as we can see. Still, the auto-martingale difference divergence function does not find dependence, and this makes us think that the series are a martingale difference sequence. This is also representing the test. These are the p-values of the two tests, Fockiano's test and our test statistic. The Fockiano's test rejects the null hypothesis of independence. We are not basically we can say that we cannot say that the series are a martingale difference sequence. Okay, and that's it.
Well, I have my question. So after you before, so you show that if you consider a martingale difference sequence as a simple Gaussian model, no? We know that if we observe the parallelogram of this series, we found that is similar to white noise because we don't find any correlation in the parallelogram. But we also know that if we check the square series or the absolute series, then we find some pattern in the parallelogram, okay, in the case of a Gauss. What I would like to ask you is what's up if you apply your form of autocovariance to the square or to the absolute series?
No, in that case, there's also linear dependence, so everything is already known by the beginning, because this works when this is useful when you do not have any form of linear dependence, and so you can find something additional. But in that case, with squared series, you already have linear dependence. So linear dependence is found, and then also no linear dependencies.
Okay.
Let's say also this opens the possibility that also no linear dependence is found.
Okay, so because in the case is non-linear dependence, we consider the square, no?
Yeah, exactly.
Okay.
No, not in that case. I mean, the statistic also finds linear dependence.
Okay.
The important thing is to detect some form of dependence with zero autocorrelation. If autocorrelation is already there, you already know that there's a dependence. What you want to explore is the case in between.
Okay. Yes, understand. What?
Yes. This finished. Okay, so. Are there any questions from the audience? I don't know. Else?
Yes, I have a question. I don't know. Is it finished? Or?
Yes.
Yeah.
Okay. Thank you for the talk. I have a question about the bootstrap that you use for your test statistics.
Yes.
So it seems that you use the independent white bootstrap. Is it the bootstrap that is really adapted to the setup, or do we have, for instance, consistency properties of this bootstrap? Or?
Okay, the paper is. Sorry, I can't remember the exact paper, but yeah, this kind of bootstrap works well with this kind of statistics because these are use statistics. This is the exact case in which this kind of thing work. The paper I can't.
So even if there is no independence, but there is non-correlation.
Yeah. This is also, yeah, exactly. That's a good point. For example, with this kind of bootstrap, you can allow for some dependence in the auxiliary variables, the vectors that you collect and you pre-multiply and post-multiply for the double-centered distance matrices. And as you collect the auxiliary variables, you can introduce some form of dependence, and actually you can formulate, there's an exact formulation, but it's kind of like an autoregressive link for the auxiliary variables. So you can allow for that as you are testing for martingale difference for the martingale hypothesis, let's say.
Okay.
Yeah.
Maybe the question of Lionel was because we did some work for extending the white bootstrap for dependent random variables, and so maybe it was what you were thinking about. Or?
Yeah. The question was to know if there is a martingale difference process. So because it's called the wild independent bootstrap. So I suppose that when the data are dependent but without martingale difference, maybe it's not a good bootstrap. But I was asking if when there is dependence but martingale difference, this kind of bootstrap is adopted. This was the question. Maybe yes.
Yeah, it becomes better by allowing this dependence in the auxiliary variables. In that case, you generalize it, and it's more appropriate for testing for a martingale difference sequence in that case. But for example, what Phokianos does is testing for serial independence, so he can just take all the auxiliary variables to be independent, and exactly I do exactly that for testing for a martingale difference sequence. I allow some dependence.
Yes. Because in the case of Phokianos, under the null hypothesis, you have independence. So the usual bootstrap for independent data.
Yeah, and allowing for, and I didn't report the results here for the dependent case. In the end, they are very similar to the independent case, but basically, yeah, I tried to do that to allow some dependence. I can also look for the exact paper. No, it's not. Just 1 second. I can. No, it's not here.
It is not the paper of Newman. No.
Maybe Leukten Neumann.
Newman. The German. Yes, he make a paper with a wild autoregressive bootstrap.
Yeah, that's it.
Okay, so
that's Leukten and Neumann 2000 something.
I don't think that is your name. I remember just
I had a paper with him on white bootstrap for dependent data. Okay. So maybe we just stop recording now. Yeah, it doesn't make sense, but we can go on discussing if you want. I just cut the recording.